Good evening, guys. I guess I am audible to all of you. Just give me a little bit of feedback about my voice right now. Is it clear, loud? Perfect. Great. Okay, guys. So thank you, Suraj. Thank you, guys. Now, let's get started. Right? Turn on your cameras and make it quick. Okay. So I guess you know the agenda for today's session, guys. It is we are actually going to talk about the entire is block today, right? Now here, okay, the version confused and others. Don't make me looking, guys. Keep your cameras on. So today we'll be actually talking about, guys, mainly the S block. Now, in the last class we have been talking about hydrogen, right? And there, I guess you have seen that the chapter is solely based on the similar kind of topics that you have been learning in grade 10 and in the younger classes as well. Were some pretty new things for you as well, but more or less, like in inorganic chemistry, there are gonna be a lot of reactions and stuff. But I would suggest you not to kind of remember all the reactions over there. I would it would be more easier for you when you are actually going through the conceptual approach towards science, towards each and every single reaction. Okay, today as I have actually seen that in yesterday's webinar, it has taken a little more than usual time in order to complete the entire chapter. So today my approach will be a little bit different in order to complete this entire thing in a particular given time. So guys, first I'll be teaching you all the concepts which is related to this chapter. Okay. So whatever concepts are there in this chapter, first I'll be teaching you all those things first, and then I'll be going for the all the reactions and everything. Those are there in the entire chapter, so that you don't get that much of doubts like you were having, in the previous classes as well. You have seen that some new things coming in, and in those situations, things are a little bit getting delayed in there, right? So because of that, today first the concepts, and then guys we'll be moving forward. Now, about the concepts also, you know the most of the concepts that I'm going to talk about today. But there is one thing that is there in grade 12, um, electrochemistry chapter. That concept is something that I have to teach you first before I go for the entire explanation of this chapter. Okay, and I can see that many of you haven't turned your cameras on yet, guys. Please make it quick. Prashita, Rahul, okay, guys, Pratyush. All right, so let's get started from here then. Make sure, guys, whenever you're texting something, you are sending it in the notes account. Now, so over here, I need a blank space for the concepts. So, guys, in this chapter, now, I mainly need two major concepts. And both of the concepts you are pretty much aware of. Let me check the lines. Yeah. So, like I was saying now, so both the concepts that I'm going to talk about, we are pretty much aware of both the concepts. Uh, to be honest, one of the concepts is very much familiar to you, which is the Fajans rule. I guess all of you are pretty much aware of what Fajans rule is. The second concept that I'm going to talk about is, guys, the reduction and the oxidation potential. Okay, this is actually coming from the chapter electrochemistry of grade 12, but This is so you can understand we are also going to have a kickstart towards the grade 12 chapters right now here as well. Okay. Now, let's start talking about the Fajans rule once, because this is one of the, yeah, the electron potential. Exactly. Got it right. Once. Right. So did you send us? Arnav, I am yet to do that. I'm going to do that. Okay. Don't worry. And those who haven't turned their cameras on, guys, let me know the reason. Okay. Now, guys, the first thing is definitely the Fajans rule. Now, before I start talking about this rule, I would like to see how much you know about this. Okay. So let's say, guys, I'm gonna ask you one question here. First, what is the Fajans rule gonna talk about? Like, what is the outcome of Fajans rule or use of Fajans rule? We get to know the ionic and covalent character in a compound. Ionic or covalent character in a compound, right? Right, exactly. Now, other than that, guys, other than that, what else connecting questions can be formed from here? So they can clearly ask you straightforward ionic character, covalent character questions, or which they do not really ask you in this way. They rather ask you in terms of melting point, boiling point. Now, guys, you can clearly understand if a particular compound is ionic in nature, then its melting and boiling point would be high. If it's covalent in nature, it would be low. Simple. Or they can also pose this question with respect to solubility. So, guys, you know that if I'm talking about an ionic compound, it would be soluble in water. Otherwise, if I'm talking about a covalent compound, it won't be soluble in water, right? So, Fajans questions can be asked in these different ways. Okay. Now, let's say, guys, I'm asking you a question over here. Let's say I have Li F and Li I. Would you tell me which one of these two is more ionic in nature? Which one is more ionic in nature? Guys, both of them are ionic compound, right? Metal, non-metal, so both of them are ionic. But which one has more ionic character in it? Comparatively, which one is? Come on, write it down now. Let me see how many of you know this. Okay, I'm gonna take the names of the students, those who have given the right answer so far. So Apratim, you're the first one with the perfectly right answer. Then I have Mahek, then I have Daya, and I have Samia with the right answer. Devashir, you are also right. Rahul, that's the correct answer. Rashida, that's right. Swaraj, Pratyush, Ritik, Rohit, um, Arnav, Sean, Tarang, and Spriti. These are the right answers that I have got so far. The rest of the answers are not right. And what about the rest of you, those who haven't answered so far? Ashwin, Vishal, Shrutika, think a little bit more. You are close. Shivani, that's right. Ashwin, that's right. Very good, guys. Very good. Keep trying. Om, what about you? Okay, guys, I'm going to wait for a few more seconds before answering the question. Said that's right. Okay, great. Guys, so the answer to this question is LIM. Okay, so the first one to write the answer was Apratim. Apratim, would you go ahead and explain this for me? Why is it LIM?
So lithium is common in both of the molecules and flow. If you look at the anions, F minus and I minus. So if you look at the fluorine and iodine, iodine is bigger in size. So we're going to use the rule that the larger the size of the anion, the more covalent character, because the orbitals are more easily polarized,
You
as
use
the
this
pull of the
terminology that
nucleus is not as strong.
polarizability is high, right?
Yes, sir.
Correct. If it is highly polarizable, then it's highly more covalent in nature. So, guys, what is happening over here? See, lithium is common in both the cases, right? So now, let's say this is my lithium cation, and this is my I minus anion, and this is my lithium cation, and this is my Cl minus anion. So you can clearly understand if the anion is bigger, that means you can easily distort the electron cloud because the electron cloud is so much far away from the nucleus. So you can easily distort it, right, Anish? Right, Swaraj? So as a result, it would be overlapping with the lithium's atomic orbital, and the moment it does, it would become covalent in nature. It would generate covalency in its nature. So as a result, guys, an ionic compound can also attain some sort of covalence inside it. So that as a result, this LiF is more ionic than LiI. LiI has generated some covalency in it, right, guys? Clear about this? So now, if I ask this question in another way now, if I ask who would be having more melting point, boiling point, so guys, the answer is going to be just the same. If this is my ionic compound, then the boiling point, melting point will be high for it. Correct, guys? In that way, we are going to answer this one. So this is one thing which is known as Fajan's rule. The other thing, other concept that I need from you is electrode potential. Is there anybody who is aware of this particular terminology? Electrode potential? Raise your hands. Concept of electrode potential and how does it work? Anyone? Okay, just tell me what you know about it, April.
So it's like it's a measure of how the oxidative or reductive nature. So like if it's like oxidative nature is very high, then if it's like a good oxidizing agent, then its tendency to get reduced will be also very high. So the reductive electrode potential, that would be high,
You're kind
if
of
I
correct
remember.
on. You're kind of right only. I'm going to explain this thing to you guys now. Okay, just give me 1 second. Then I'll be back. Just 1 second. All right. Like I was saying now, guys, what is this electrode potential here? So electrode potential is something that helps you exactly with it. Electrode potential is something that helps you to understand whether a particular species is oxidizing or reducing. So right now, if I ask you this question, do you know out of the, let's say, out of all the elements those are there in the periodic table, who is the most oxidizing element and who's the most reducing element? I can give you a hint. If I'm asking for the most reducing element, guys, that means it is going to be from the metals. Who's the most reducing metal? Anybody?
So can you check?
I am. Okay, many of you have given the oxidation one correct. Tarang, you are correct in both the cases. Ritik, you're the first one to write the right answer for oxidizing agent. Tarang, you are right in both of them. Apatim, you are right in both of them. Then Ritik, you are also right. So, guys, the strongest exact is Pratik. Very good. Sean, that's very good. That's right as well. So, guys, what actually happens is in the entire periodic table, lithium is the most reducing agent and fluorine is the most oxidizing. Very good, Ashwin. Say that also. So, guys, now this is for the fact you know it. But in electrochemistry, there is something called electrode potential through which you can get to know the numerical value of all of them. Guys, keep your cameras on. Now, if I'm talking about the electrode potential over here, what do I mean by that? Let's say there are two ways of representing the electrode potential. One is E naught M2 plus M. Guys, this is the way of representing the reduction potential. Why? Because you can see M2 plus is turning into M here. And how would it turn? By taking two electrons, it would turn into M. So M2 plus plus two electron turning into M. This is a reduction process. So from here we can conclude that M E not M2 plus M. If I write it like that way, that means I'm talking about reduction potential. Simultaneously, guys, if I write E naught M2 plus, that means I'm talking about oxidation potential. Because which reaction am I talking about here? I'm talking about M is getting converted into M2 plus. This is an oxidation method, right? This much we are clear. Now, let's say I am giving you a value that E naught M2 plus M is minus 3.05. What do I mean by that? So, guys, if I tell you, you have JE, let's say you have JE cracking potential is negative. What do I mean by that? That means you won't be able to crack J. If I say this to somebody, that means you won't be able to crack J. If I say you have a positive potential, that means you would be able to do, right? So the moment I'm saying E naught M2 plus M is a negative value, that means, guys, this reaction is not gonna happen because the potential has been found to be negative. Correct? Understood, guys? So which reaction would happen then? If you turn the reaction around now, so if I turn it into oxidation potential, this value would become now positive 3.0. So oxidation reduction potential, you can just turn it around as well. So now over here, it would be positive 3.05. That means M2 plus M reaction is not going to happen looking at the negative value. Here it is positive value, that means this reaction is going to happen. Are we clear so far, guys? This is how we are going to, yes, it is exactly from the redox chapter. You are correct. So do we precisely mean not going to happen, or is it? No, it's not going to happen, Suraj. Okay. Whenever the potential reduction potential is negative, it's not going to happen because see, it has clear connection with thermodynamics. Delta G can also be written as minus N into F into E cell. So if your value is negative, so delta G would be positive, so the reaction won't happen. If your E cell value is positive, then only the delta G would be negative, right? So that means the reaction would happen spontaneously. In that way, it is split. Okay, guys. So far, we are all clear. So this is all I needed to tell you here. So now, one more thing before I start the chapter. Whenever I'm not mentioning it, let's say I've just written the E naught value of lithium is minus 3.05. Remember, I'm talking about reduction potential. I'm talking about reduction potential. In this chapter and even beyond, even in the chapter electrochemistry as well, guys, we only talk about the reduction potentials. We never talk about oxidation potential. Okay, reduction potential is going to be always the method of solving every single questions of electrochemistry as well, right? So now, with this much of concept, we are going to start this chapter. So guys, make sure that you have noted all these things down. All clear, guys? No such doubts anymore. All right. Only the conceptual part, if you could note it down, that would have been better, but it's fine. Anyways, it is there, and I'll be sharing this with you. And if I've
Excuse me,
understood,
sir.
then that's fine. Yes.
Sir, I was just disconnected for a while. Can you give me a small recap what we did?
For the entirety of or the inner potential only. What have you missed? Tell me, what is the last thing that you heard?
Sir, we were starting with the we were doing the lithium one question after that.
Lithium question means
Lithium, sir, about the where we were
this one.
Fajan. Yes, sir, Fajan Sul.
Okay. But in that case, now I guess we have to sit in the end of the session. I guess we missed the discussion yesterday as well, right? You had some questions for me, and I guess I missed that as well. As it is streaming live in the YouTube, that's why I cannot turn it all over again. So you just stay after the session, no issues. We can talk about
Okay,
it.
sir.
Okay.
Okay, sir,
All
I
right.
will watch it.
If you can, that would be better. Or if you can
Is it,
talk, if you want, you can talk to me as well. Okay, no issue.
sir, on what
Anyways,
channel is?
right now it is in the askIITians YouTube channel only. It is live in there.
Okay, sir.
All right. Anyways, guys, just a quick recap for Pratyush over here in the end. But the major topic that I have been talking about is the electrode potential. The electrode potential is something which tells you about the oxidation or reduction tendency of somebody. So if I'm writing E naught potential M2 plus M, that means I'm talking about reduction potential because the reaction that it is trying to convey is M2 plus turning into M. Correct? This is what it is trying to tell. So this is the value is given as negative 3.05. Whenever the value is given in negative, that means, guys, this reaction won't happen. Okay, whenever the values are positive for E cell, that is when the reactions are going to happen. So as you can see, E naught M2 plus M is given as negative. That means M2 plus turning into M, this reaction is not going to happen, Pratyush. On the other hand, if I turn this reaction around, let's say E naught M2 plus, then we are going to call it oxidation potential, because here the metal is turning into M2 plus. So it's an oxidation reaction. So now that value would be positive 3.05. So negative 3.05, if you turn it into oxidation potential, it would be positive 3. Correct. So now this reaction has a positive E cell value. That means this reaction is gonna happen. That's all I meant to say. And in this chapter, guys, we are only gonna talk about reduction potentials. They won't be mentioning what kind of potential it is. They would be just calling it E cell, but you just know that it is oxidation reduction potential is what we are talking about here. All clear now? Pratyush, is it clear?
Yes.
Right. That's all I need. Now, let's start this chapter now. So, guys, this chapter is pretty much easy with respect to all the inorganic chapters that you have ever learned. If you just listen to the group one or the first half of this class before we go for the break, the second half of the class would be something that you would be able to also interpret. Okay, I don't have to teach you that segment anymore. So I want you to be very, very attentive in the first half of the session. The next half would be very simple to you in that case. Okay, right. So if I'm talking about group one element, guys, first we'll be talking about group one element, then we'll be talking about group two element. Because when I'm talking about S block, when I'm talking about S block means in the periodic table, we are talking about group 1 and group 2 elements, correct? Now, so guys, with respect to which all elements are present in group 1 and group 2, so it goes like lithium, sodium, potassium, cesium, rubidium, cesium, francium. And in group 2, beta, manganese, car, sugar, ras, right? I guess you have these kind of mnemonics to remember all of these groups in there. Now, guys, we need to remember all these elements in order to go forward. Now, if I'm talking about group 1 element, that means their common electronic configuration is ns2 1. So if I'm talking about, okay, hydrogen is also a part of group 1, but we don't talk about hydrogen in here. We start from the lithium. That's why we call it alkali metal, right? And you know, group 2 is also known as alkaline earth metal. Alkaline. So we are not going to talk about hydrogen throughout the time. All right, guys. Now, so the electronic configuration for group 1 elements would be ns1 and group 2 elements it would be ns. Like example sodium. Sodium, you know, its atomic number is 11. So the electronic configuration is 1s2, 2s2, 2p6, cs. So ns, correct? What would the potassium be? 4s1, 5s1, 6s1, 7s1. It goes on like that. Right? Simple, guys. Now, atomic radii, if I talk about that, see, these are all periodic properties things. You have learned it in periodic properties only. Atomic radii, guys, you tell me what happens when you go down the group. Your atomic size increases, radii size increases. We all know this already, right? So lithium to francium, the size of the atom would increase. By the way, guys, out of all these elements in here, this guy is radioactive. Okay, francium is radioactive with nature out of all of them in here. Now, lithium to francium, the atomic size would increase. Correct? We all know this, learned it in grade 10 only. Now let's talk about ionization enthalpy. So that is also very, very known to us. What is ionization enthalpy, guys? The enthalpy is another way of saying energy. They are not exactly the same thing though, guys. But you know, they may, try to mean the same thing. So if I'm talking about, exactly, Apatan. If I'm talking about ionization enthalpy, that means, guys, I'm talking about the energy needed to release the outermost electron. If this is my valence shell, the energy needed to release the valence electron, that is called ionization enthalpy. Now, as you know, lithium to francium, the size is increasing as we move down. Exactly. The size is increasing. That means, guys, let's say we talk about a small atom, we talk about a large atom. Now, what would happen to the ionization energy? So small atoms, they are closer to the nucleus. So it is very, very difficult to take the electrons out. But when we talk about the large atom, you can understand the electron is far away from the nucleus. So it is very, very easy for us to take out the electrons out here. So when you move from top to bottom, the ionization energy means the energy needed to take out the electron, it is gonna be decreasing. It will be easier for us to take out the electron. What is the effect? What is the use of this particular theory that we have learned? It is called photoelectric effect that you have learned in atomic structure. You remember, guys, which all metals are gonna give you photoelectric effect experiment? Francium, potassium, cesium, these people, na? So why is that? Yeah, cesium. So why is that? Because the moment the light falls into the metal surface, they would be leaving the electron. Now, why are they leaving the electron? By just for placing some light on it, because they are asking for very low amount of ionization because of that. Right, guys? Are able to connect all these things now? Now, moving on to the hydration enthalpy. Guys, hydration enthalpy, it's a very, very important topic in terms of not only the S block element, but also the going forward in the all the inorganic segments as well. Hydration enthalpy is the energy released. The energy released. Guys, specifically the energy released. Okay, it's not endothermic. Hydration enthalpy is always exothermic. Remember this one. Okay, energy released due to hydration. Energy released due to hydration. That is called your hydration enthalpy. So it's always exothermic. Okay, guys. Right, Apath. Very good. I'm gonna ask you one question from here actually. Now, if I move from top to bottom, if I move from top to bottom, what actually happens is, guys, see, the lithium is the smallest in size, francium is the largest in size, correct? Now you tell me, let's talk about when you are trying to dissolve something in water. Let's say you are trying to dissolve a sugar cube in water, and on the other case you are trying to dissolve some, you have seen those packet sugars that comes in whenever you are not traveling by traveling through the flight or train. You have seen that they give you those powdered sugar, right? So now you think about both the situation. In one case you have the powdered sugar, and the other case you have the other sachets. Exactly, you have the powdered sugars, in the other case you have sugar cube. Which one would dissolve easily in what, in any solvent? Definitely the powdered ones, because the particle size are smaller there. So you can clearly understand from your common sense only that the smaller size are more soluble in nature. So from there also we can come to the conclusion that, guys, that lithium is the most soluble, francium is the least soluble. So now if I ask you what would be the hydration enthalpy trend in here, see, if it is the most soluble, that means, guys, this is gonna be the delta H hydration, means the heat of hydration would be very, very negative, highly negative. Negative means, guys, exothermic. Don't get confused, right? This negative and not negative. Here, negative means exothermic. More negative means it's better, right? It is releasing more energy means it's better, right? Now, so this is highly negative. Now, more you go down, the negativity decreases, the exothermicity decreases, so the hydration enthalpy decreases. Hydration enthalpy decreases, right? Here the hydration enthalpy will decrease. Now, I have a small question for all of you here. Let's say, guys, we are talking about, this is a very important question over here. So with lithium, we get more energy release. Exactly, exactly. Lithium would be releasing more energy. Cesium, francium would be releasing less energy. Okay, less negative. Okay, guys, enthalpy decreases means it becomes less negative. Okay. Now, let's say I'm talking about, guys, I'm talking about size of group 1 element. Okay, listen to this question very carefully. I'm talking about size of group 1 element. Let's say I'm talking about Li plus, Na plus, and Cs plus. I have these three atoms. So now, guys, you tell me what is the size order? Definitely, from top to bottom, the size is gonna increase. Correct? The size order. Now, if I ask you the same question, size in aqueous medium. If I ask you the same question in this way, size in aqueous medium. So guys, you have to tell me about the size of Li plus, Na plus, and Cs plus in aqueous medium. What would you say in this situation? See, now here, perfect answer. So here what happens is, guys, lithium gets hydrated the most. That means, Anish, many water molecules would be accommodating around lithium because it has high hydration enthalpy. Correct, guys? As it has high hydration enthalpy, right, Samya? As it has high hydration enthalpy, it will be accumulating a lot of water. So the size of lithium in water would be the largest. Did you understand this point, guys? Lithium alone is small, but when you are dissolving in water, it is accumulating a lot of water molecule. So in aqueous medium, Li plus has the largest size, and Cs plus, it would be accumulating very less amount of water particles around it. Exactly, Ashita. It has been experimentally seen that it is like the lithium is larger in size. Okay, all right. Now this is gonna be. If you have any doubts, guys, do send it over to me in my host account, and those are watching live in the YouTube, in the chat comment section, you can send it as well. Okay, hi Pushan. Now have a look, guys. Here, so the hydrated radius, if I say, then the order goes like from top to bottom, the size is decreasing. Friendship ended in physical chemistry, now organic is my favorite topic. All right, Utpatan. It was my favorite topic as well. It is actually. Now have a look at again, guys. Here, so the hydration enthalpy thing is now, I guess, clear to all of us. Now this question can come in another way, guys. The question can be given as, so over here, Vignesh, it is being asked like, let's talk about the ionic mobility. Ionic mobility of group 1 ion in aqueous solution. This question can also be asked in a different manner. So they're asking you what is going to be the ionic mobility of the group 1 ions in aqueous solution. So guys, try to understand, if you're bigger in size, then definitely you won't be able to move faster. Your movement would be slower, Sean. So from there, can we come to this conclusion that lithium in the aquated state is going to be least mobile, and cesium in the aqueous state is going to be the most mobile? The ionic conduction, ionic mobility, these three things would be most for cesium and these for. Correct? Exactly. But in gaseous phase, what would happen, guys? The opposite. Because in gaseous phase, the size of lithium is smaller, so it would be moving faster. Like, all clear, everyone, guys? Okay. Now, coming to the next one, chemical properties of here. Guys, chemical properties are something that I guess even without my help, you can solve these questions. So you tell me now, if I react these people with oxygen, what am I going to see? We are going to see their oxides, right? But there is one twist in the story over here. For lithium, we see oxide. But for the sodium, we don't see oxide. If we react it with oxygen, we see peroxide. Correct, brother. And for potassium onwards, cesium, francium, for them, we see superoxide. This is called superoxide. This is called peroxide. This is oxide. How do I know all this? How do I know all these things, the names and all? Because, guys, here the oxygen is in -2 oxidation state, whereas here the oxygen is O2 2 minus. You can see O2 2 minus. That's why it is accommodating two sodiums, two Na plus, O2 2 minus, right? And what is the ion over here, guys? O2 minus. So O2 minus is oxide, O2 2 minus is peroxide, O2 minus is superoxide. Okay, this is superoxide. Now, guys, why is it like that? I'm gonna put you on hold for that because this is gonna be discussed later on in the notes. So I'm gonna talk about Ashita, even not only the structure, beta, I'm gonna talk about the entire molecular orbital theory of these three things. Okay, it is there somewhere there in the bottom side of it. You can see over here. Even the emo theory and the reason and logic, everything would be discussed now. Okay? I don't have spaces in this part actually. I've kept some space in the bottom side. Now, have a look, guys. Now, there is one special thing about lithium, guys. Not only lithium, there are one or two more people out there, those who can do the same thing. So, guys, lithium can react with nitrogen. Now, there are very few people, those who are capable of reacting with nitrogen. Now, what is the logic behind this? Guys, nitrogen acts like a noble gas because it has three bonds in between them. Now. So, there are very few metals, those who are capable of breaking all the three bonds in here. So do you know that when I used to even this moment as well, whenever I am doing any, let's say, any performing any reactions in lab, I if I do not have, if in most of the labs, guys, what they do is they don't always have noble gases around. So instead, they can also do the same kind of reaction with nitrogen gases because nitrogen gas acts like gas because they are not at all, reactive because of the triple bonds in there, and it takes an immense amount of temperature, immense amount of energy to break them. So that's why, guys, we can also use nitrogen as a noble. That's why only lithium and magnesium and beryllium, not even beryllium, lithium and magnesium mostly, these two are capable of reacting with nitrogen. Now that is also not something that you are learning for the first time, guys. You already knew that there is something called diagonal relationship, isn't it? So lithium and magnesium, they are on the diagonal relationship. So whatever lithium can do, the similar things would be done by magnesium as well. So always remember, guys, reaction with nitrogen cannot be done by all of them. Only lithium and magnesium can efficiently react with nitrogen. Okay, this is the thing. Now, what is the oxidation state of oxygen in KO2, guys? Give me the answer for this. And please keep your cameras on. This is the third time I'm asking you to do this. Come on now. Every one of you, figure out the oxidation state of oxygen over here in potassium superoxide. Rohit, Arnav, Shrutika, Smriti, quickly. Guys, I got only 10 answers so far. All of them are right. Be quick now. It's a very simple question. So how do you answer this question, guys? First, you write KO2. I'm asking for the oxygen state of oxygen over here to take it as X. Potassium is a group 1 metal, so it will be plus 1. So plus 1 plus 2x. Two oxygens are there, right? So that would be 0. So X will be minus half. So in the superoxide, guys, oxygen oxidation state is minus half over here. All right? Not minus 1 beta, minus half. All clear? Now, moving forward over here, reaction with water. So guys, this is something I guess you have learned in yesterday's session as well. What happens when metals react with water? You get metal oxides, metal hydroxides, and hydrogen gases. Who gives oxide? Whenever we are talking about some reactive metals, they give oxide and hydrogen gas. But when we are talking about less reactive metals, remember for iron what happened? Fe3O4, right? Ferrospheric oxide, not hydroxides there. So here also I get lithium oxide because lithium also is a very strong metal actually. So LiOH and hydrogen gas out. Now guys, in here, you already know that lithium, there is something that I wanted to tell you about this lithium's reactions perspective over here as well. Always remember one thing, guys, not only for group 1, I'm not really talking about group 1 or 2 over here. I'm talking about all the group chemistry that you're going to learn in grade 12 as well. For all the group chemistry, always remember, guys, the first element. So for group 1, it is lithium. I'm going to teach you group 2 there, it would be beryllium. Then for group 13, it would be your boron, then carbon, then nitrogen, then oxygen, then fluorine. For all of them, there'll be one thing common. They would be anomalous in nature. What do I mean by anomalous, guys? They are not going to act the same way the rest of the group elements are going to. I'm going to talk about this in details. First thing is, guys, they are very, very less reactive. They are kind of inert, the most inert element of that. Now, why is that, guys? Because clearly because they are the smallest in size of that group. Group means these people, the people beneath it. With respect to them, the first element would be the second for every one of them. Okay. With respect to the entire group, actually, Shika, lithium would be the smallest in there. If it is the smallest, guys, it would be asking for high ionization energy, right? It will be asking for a lot of energy in order to take out the electrons, right, Samya? So as a result, guys, it would act like a little less reactive. So for other elements like sodium, potassium, cesium, francium, they would react immediately with water, not lithium. Lithium would take a little bit of time for the reaction to happen because it's a less reactive. All right. There is one thing that you need to know about lithium, guys, that lithium compounds, if I talk about, let's say, LiCl2, lithium compounds are always found in hydrated state, always, because the hydration enthalpy of lithium is very, very high. We have just talked about this. So as a result, later on also I'm going to talk about these things. That's why we have seen that lithium halides are always found in the hydrated state. Okay. Now, moving on to the next reaction with dihydrogen. This is also something, guys, that I have taught you in the yesterday's session. Whenever any metal reacts with hydrogen, you already know that what happens, guys. Under the presence of high pressure and high temperature, they form metal hydrides, right? Remember, I taught you in the last class. They are called ionic hydride or saline hydride, and we get hydrogen in a negative format in there in yesterday's session. How come lithium only alkali that reacts with nitrogen but doesn't react as much as so Sean, what actually happens is, see, they when I'm talking about lithium and nitrogen reaction, so over there, what actually happens is the electropositivity of lithium is the thing that is working. When I'm talking about breaking of bond, let's say I'm talking about nitrogen bond is being broken. For the rest of you guys, what's the question Sean is asking? Sean is asking that if lithium is not that reactive, then sir, how is it reacting with nitrogen and other some? So guys, when I'm talking about the formation of this compound Li3N, what actually happens is the theory goes like this. In order to break this N triple bond, you need a lot of energy, correct? In order to make this N3 minus. Now that much of energy can only be compensated by Li because of high electropositivity present in the lithium. You have only written that in the chat in the beginning that lithium is one of the most strongest reducing agent, right? Right. You have written in the chat today. So guys, what is happening to nitrogen when it is making Li3N? It is getting reduced only, right? So lithium being a very strong reducing agent, it is acting as a reducing agent in Li3N as well, and it is breaking it down and making it N3 minus, right? So that's the same concept going on, right? Now, coming to this part, guys, reactivity with dihydrogen, so they make hydrides. So if I talk about potassium with hydrogen under high temperature and high pressure would make potassium hydrides. And the details about hydrides is something that I taught in yesterday's session, guys, right? The ionic hydride, how do they react, and how do they found in the cathode and anode, like what is the reaction in cathode and anode, and everything has been detailedly discussed about the hydride. The only thing that you need to know is here we get ionic hydrides. Exactly, sir. K plus and H. All right. Now coming to the halogens. So guys, first of all, for halogens, you can clearly understand I'm talking about fluorine, chlorine, bromine, iodine, and their compounds over here. With all these people. With whom am I talking about? With group 1 elements I'm talking. So let's say I'm talking about lithium fluoride and lithium iodide. So today only, guys, you have told me, let's say lithium fluoride, lithium bromide, and lithium iodide. So what kind of question are gonna come from here? Questions related to covalence. So in today's session only, so I guess Pratyush, you have missed this part over there. So this is another recap of that. So over here, guys, what actually happens is because of Hajan's rule, you know that lithium fluoride is the most ionic of all, and lithium iodide is the least ionic, or you can say it has a high covalent character generated in it. This is the kind of question that they can ask you guys. It is straightforward from Pajan's rule, and they can also go like, let's say now, CSF, CSPL, CsBr, Cs. Here, guys, if I ask you which one is the most ionic, which one is the least ionic, the answer is going to be just the same. CsF is going to be the most ionic, CsI is going to be the least ionic. How do you solve these questions? Guys, if the metal is same, to get rid of it, no? Answer is going to come from the anion set. Now you see which anion is the most polarizable. Guys, bigger the size of the anion, it is more polarizable. So guys, iodides are always going to be more covalent in nature. Fluorides are more ionic in nature. Now if I change it around, let's say I've given you a question where I'm talking about lithium fluoride, sodium fluoride, and let's say potassium fluoride. Now tell me in between these three guys, which one is the most ion in nature? Lithium fluoride, sodium fluoride, potassium fluoride. Which one is the most ionic in nature, guys? I'm getting a lot of wrong answers over here, guys. Do cross check your answer one more time. So here, what is common? Tell me. Here, the anion is common, right? So get rid of the anion. Okay. So Li plus, Na plus, K plus. Now, guys, for anion, for cations, what we look for? We look for polarizing power, right? We look for polarizing power. For anions, we look for polarizability. Here we look for polarizing power. So who got more polarizing power? If the cation is small in size, that means, guys, it has high charge density. If it has high charge density, it has high polarizing power. The lithium has the highest polarizing power. Potassium has the lowest polarizing power, right? So polarizing power is decreasing down the group. If it is decreasing down the group, that means, guys, potassium having the lowest polarizing power, it would be having lowest covalence, correct? So potassium fluoride is gonna be my most ionic. One more time, guys. When we are moving down the group, we are increasing the size of the cation. The charge is just the same, right? So if the size is increasing, then the charge density, what is happening to that? Charge density, if the size is increasing, then the density is decreasing. So if the charge density is decreasing, then the power to polarize the anion is decreasing. The power to deform the anion electron cloud is decreasing. Right, guys? Clear so far? If it is not being able to polarize the electron cloud, if it is not being able to polarize the electron cloud, it would be more ionic in nature. This I'm talking about a small cation and an anion, a large cation and an anion. Who would be attracting the electron cloud more? The small one would be attracting the electron cloud. The large one would be attracting less. Because the density is less in here. Charge is same, but the density is less. This one would be more covalent in nature. This one is more ionic in nature. That's why Kf is more in nature. All right, guys, clear so far? So this is going to be our answer for this question. Now, moving forward, guys, reducing character. See over here, this is what I was talking about. There is a list given in your NCRT as well. E-naught value. When I'm talking about E-naught value over here, high polarizing power means more covalent. Exactly, Smriti. If you are polarizing more, definitely you are overlapping more. If you're overlapping more, then definitely you are more covalent in nature. Correct? Now, have a look, guys. If I'm missing any of your doubts, guys, just write it down and make sure that you're sending it to the host account, okay, not the co-host. Okay. Now, see, if I'm talking about E-naught value, guys, what am I talking about? I'm talking about reduction potentials. I already told you. For lithium, it is 3.05, and this is how it goes down. Okay. You can see that more you are going down, the E-naught value is decreased. Reduction potential is decreased, right? And oxidation potential is decreased. So the reduction potential is decreasing when you're going down there, right? So on the top of this list, you have lithium, which is the most reducing agent. Now, when you go to the extreme down of the group, this is not given till the end. If you go to the extreme bottom of the group, you will be finding fluorine in there. This entire group is there, entire list is there in your electrochemistry chapter. Okay. Now, there is something that you need to notice over here, guys. You might be thinking that lithium is the most negative Then after that, it would be sodium. After that, it would be potassium, isn't it? But if you notice, in the entire group 1, lithium has the highest negative value and sodium has the lowest negative value of all. See, after lithium, they are giving potassium, calcium, sodium is here, minus 2.71. So guys, you have to remember this for a fact that I'm going to explain this thing as well to you in today's session only. So here, make sure guys, you know this, that lithium has the highest reduction potential in the entire periodic table only, not only in group 1. Highest reduction potential, and sodium has the lowest reduction potential in group 1. In group. So lithium is not only having the highest reduction potential of that group, it is also having the highest reduction potential of the entire periodic table. But for sodium, what I'm mentioning, it is only for the group. It has the lowest reduction potential. Okay. Now that's the point to be here. All right. Now moving on to this next part, guys. This is the very important part, and from here we have been seeing, we have been noticing some questions coming in lately as well. What happens when you dissolve group 1 metals in ammonia? This is the same thing that happen with group 2 metals as well. So guys, let's learn it together. So for group 1 and group, for both of the two types of metals, and see, if you understand the concept now, you'll be able to understand that for 90% of the metal, we will be seeing this reaction. So what is happening over here, guys? If you see, Taran, when we dissolve any metal of group 1 or group 2, whatever it is, in ammoniated solution, means when we are mixing it in NH4, ammonium solution. So the ammoniated alkali metals are blue in color. So we get a blue colored solution. Now, what is the reason behind formation of this blue color? So they are saying that not only group 1, but group 1, group 2, and even it has been found for copper as well, D block element. Anyway, coming to the point over here, what actually happens is, if you notice in this segment here, in this picture it is written that group 1 metals, while they dissolve in ammonia, metals, they are very reducing in nature. What do I mean by reducing in nature? That means they donate electrons. Every single metals are prone towards donating electrons, isn't it, guys? Just 1 second, let me see. All right. Every single metal is prone towards donating electrons. We all know that, right, guys? Like sodium, lithium, potassium. And then again, in the yesterday's session, I completely told you this, that lithium makes the strongest reducing agent of organic chemistry, lithium aluminum hydride, right, guys? So they are very prone towards losing the electrons. Now here also you can see that sodium is losing its electron in the solution. Now this particular electron that you see, it is getting dissolved in ammonia and forming an electron ammoniated solvated compound. It's not like, guys, you have to remember the electron is surrounded by 6 ammonia. It's not like it is surrounded by 6. It is surrounded by some amount of ammonia particles that is not necessary to know. And this is not something which has been counted or quantified. Okay. So it just gets dissolved in the ammonium solution. Now, guys, whenever there are free electrons, they are capable of showing color, right? Free electrons, they make transitions in order to show color. So the blue color is coming because of this free electron, those who are ammoniated or solvated in this. So you can understand for most of the metals, this can happen because most of the metals, they are prone towards leaving the electrons, right, guys? So the same thing would be happening in group 2, whatever you are seeing right now. That's the concentration of, yes, exactly. And that is also given over here, Apratim. I'm going to come to that part as well. So Pratham is saying what would happen, sir, when we increase the concentration of metal. I'm going to talk about that as well. See, so first what actually happens is the electron get dissolved in the ammonia and it makes a complex. Let's call it ENH3 whole X. I'm putting a minus charge over here, guys, because the electron charge is minus. Correct? Because of that, the residual minus charge is present. Now, this is the reason behind you see the blue coloration. But what would happen if you dissolve more metal ion in that solution? If you dissolve a lot of metal ion, would the color get intensified? No. They're saying now the color fades away. The color fades out. Now, why is the color getting faded away when you are mixing more and more metal? They are saying now this electron is unpaired electron. Now, when you are giving more and more metal, so you are getting more and more electrons, and the electrons are getting paired up. You know, guys, the color can only be shown by paramagnetic substances, right? So when you have one electron, you are paramagnetic, but when you are adding more and more metals, you are prone towards getting diamagnetic. So as you are getting diamagnetic, you are not going to show any coloration or anything. But NH3 is base and it's actually accept photons, but metal donates electrons. So how the reaction is taking place? NH3 is a base. Smriti, over here now, we are not talking about any chemical reaction. Solvation is a physical reaction, right? So you don't consider that there is any kind of chemical reaction happening. It's just ammonia is acting like a solvent over here. So yeah, it's just a physical reaction, physical method here. We're not talking about any chemical reaction. So exactly what you have asked me, this makes total sense because both of them are bases. So definitely they are not gonna react at all. Right? You are correct only over here. Okay. Now coming back to the point again, would they form metal amide? No, beta. They won't form metal amide unless and until you give sufficient amount of energy, activation energy for this reaction to happen. If you give sufficient amount of activation energy, then definitely it can convert into amides as well. All right. So for solvation, guys, we don't maintain the temperature and pressure, right? It's just a physical method that we. Okay, guys, go through these uses. There are only one or two uses. Those are very, very important. The use number 4, sodium and lead. This particular mixture is used to make TEL. What is this TEL over here, guys? TEL is tetraethyl lead. It can be tetramethyl lead as well. Tetramethyl or tetraethyl leads are famous for anti-knocking agent. What is anti-knocking agent? So actually, guys, when we are, it's kind of a lubricant. We use it in car, automobiles. So you know, there in order to keep the engine running for a long time, we use this tetraethyl lead, which prevents the knock. Knock means the pistons. Okay, the knock created by the pistons, it can prevent that. So for that, and the aluminum is used for aircraft for this lightweight in there. Okay, so there are some of the uses that is given. This use I have talked about in the last session as well, guys. Lithium aluminum hydride and sodium borohydrates are strong reducing agent. Okay. Potassium is a vital metal for biological system over here. I guess you all know that we have a sodium potassium pump working in our body, and if we disrupt the balance of it, we would go mad because we won't be able to think straight, right? The sodium and potassium pump is what gives us the proper bet, like all the neurotransmission that happens in our body, that is happening through the sodium potassium pump only. Potassium is having a very vital role in there as well. Okay, so this is the part. Now, general characteristics, guys. Now we come to that part where we are going to talk about why lithium makes oxide, sodium makes peroxide, and potassium onwards they make superoxide. You know, guys, whenever we are talking about bonding, we need compatibility, right? Size compatibility, we need that. Correct. Now you can clearly understand when we are talking about oxide, what are we doing? Let's say this is an O2 bond. This is an O2 molecule. When we are talking about oxide, we are breaking both the bonds to make O2. Correct. When we are talking about peroxide, over there, what are we doing? We are making one of them, not the entirety of. We are just making one. That's why it is O2 2 minus. And when we are talking about superoxide, what are we doing in that case, guys? We are making half the bond, 0.5% of the bond. That's why there is only one minus charge on it. So O2 minus. So this is the partial bond work. Okay. So this is the structure of superoxide, peroxide, and oxide. Now, in the NCERT, it is clearly mentioned what is the reason behind this kind of. So, Shita, what I was saying is, when you are talking about oxide, you are going to break both the bonds of O2, the entirety of the bonds. So you get O2 minus. When we are talking about peroxide, you break one bond out, not both of them, only one of them. So O2 minus. And when you are talking about superoxide, there what do we do, guys? We partially break them, partially. Right. Now, what actually happens is when you move from lithium to cesium, guys, what is happening? The size is increasing, right? So lithium size is small. So guys, small cation would always try to bind with a small anion. More you go down the group, your size of the cation is increasing, so it is binding better with the bigger anions, right? So O2 minus is the smallest anion, that's why it is bonding with lithium. For sodium, we are getting it as it's bigger, so it's making bonding with bigger anions. For potassium onwards, it is even bigger than that. The anions are even bigger, right? So that is one of the losses. Okay, there are even vivid logics that are there. You know, lithium has been breaking the alien triple bond as well. So why not do double bond? Isn't it? It would be easier for lithium to break it for the electropositivity, right? Can we see the charge density decreases due to the capability of? Exactly. In that way, also we can definitely say that with respect to charge density method. Very good. All right, guys.
So,
This is the logic.
can you read my explanation that I sent?
Come again.
So I sent it in the chat. I think I sent it quite a while back at 8:46.
Okay. What have you sent it over here?
So 8:46.
846. If concentration of metal is very high, to become this one. Okay. O2 first electron added O2 minus, endothermic, higher ionization enthalpy of lithium. Due to higher ionization enthalpy of lithium, when it burns, the amount of energy that you get lithium to lose the electron reaction up with O2 minus one oxidation state.
So I meant -2 there.
Oxide. For sodium, ionization energy is lesser, oxygen. Exactly. So this is the exact right way of answering this question actually. So you can understand every ionic compound is being formed by the Bonhoeffer cycle. So you are just taking the help of Bonhoeffer cycle over here, right? With respect to the energy to be the overall energy to be negative, right?
Yes, sir.
Yes, definitely. But if you look at the NCERT, they are not giving it into that details. They're just saying with respect to science. Okay, and in two places of NCERT it is written in that way. But definitely the right explanation is whatever you are giving with respect to ionization energy counterbalanced by the lattice enthalpy of the compound. So this is the right way of explaining, right? Very good. Now, guys, I guess these are the things you know anyway. If I react with any oxide, if I react with water, what am I gonna get? I'm gonna get hydroxides there. Correct? Even if it is peroxide or superoxide, we are always gonna get hydroxides out. Okay. So whatever the oxide format is, when you are hydrolyzing it, you're always gonna get oxide out. Okay. Now let's talk about the next thing, which is the byproducts are not needed. When we are talking about the superoxide, guys, they're saying why KO2 is paramagnetic. In order to make you understand about that, guys, I have withdrawn the molecular orbital theory of oxygen, molecular orbital diagram of oxygen. So this is the molecular orbital diagram of oxygen, where you can see that oxygen itself is paramagnetic in nature. Let me just check one more time. 2, 4, 6, 8, 10, 11, 12, and 13, 14, 15, 16. Yes, this is for oxygen. You can see that in the anti-bonding molecular orbital, there is one electron for oxygen. This is for O2. So if I'm talking about now oxide, O2 2 minus, what would happen to O2 2 minus, guys? One electron, one electron. So it is diamagnetic in nature, right? If I'm talking about O2 2 minus is your peroxide. For peroxide, it is diamagnetic in nature. But if I ask you superoxide, O2 minus, what about that, guys? One electron, it's paramagnetic in nature. From the molecular orbital theory, you can actually interpret that. Correct?
Yes, sir.
And why do I only see 5 people turning their cameras on? What happened, guys? You already got tired? Come on, stay with me for a few more minutes and we'll be done with this chapter. The first group is only where we explain all these things in there. I wish I could read that, but as you know, Ritik, it is live stream, so I'm not gonna read your message. Why is the first one is not drawn? Not a stupid question, Smriti. I'm not drawing 1s. I haven't kept 1s because 1s is not my valence electron, valence shell, right? So I don't need it. Anyway, the valence shell is the one who is gonna react to that, right? So not needed. Even 2s was not needed either. You could have just drawn 2p. Get this. All right, guys, have a look. The delta H formation values for fluorides become less negative when we go down the group, whereas reverse is true for fluorine, bromine, and iodine. What do I mean by that? See, guys, delta H formation. This is something which have to be exothermic. Have to be exothermic. Why is that? Because you know that from thermodynamics, delta G equals to delta H minus 2 delta H. So if it is exothermic, then it is going to be feasible and the reaction delta G would be more and more negative. Chances of delta G being negative would be more. Right, Shivani? Right, Rahek? That means I need the delta H to be negative. When the delta H is negative, it is good for you. Like the bonding is strong, right? When the delta H is negative. So now what are they saying? That fluoride becomes less negative when you go down the group. That means the bond is getting weaker when you go down the group. So another way of saying is the bond is getting weaker down. Now, guys, I don't have to explain this, I guess. You can understand down down the group, the size is increasing. When you're moving from lithium to cesium, the size is increasing. If the size is increasing, then definitely fluorine is a small anion, so it would be making better bonds with small cations. So here, the delta H would be maximum negative. Here, delta H would be minimum negative because of the bond strength would definitely go down.
Sir, orbital mismatching.
Yeah. Actually, I'm not talking about orbital mismatching over here because it's not a covalent molecule. It's an ionic compound. Now. So better you take the example of lattice enthalpy. Don't use orbital mismatching. Use lattice enthalpy. So you say that, guys, that lattice enthalpy decreases because the size of the anions and size of the cation is not much, right? Won't CSF be most ionic and have the strongest bonds out of all the metals? Yes, here we are by both sides. Fine. Or CSI would be more fun can happen. No better. See, okay, there are 2 to 3 things that you have to understand over here, Sean. That when you are talking about bond strength, okay, see, all of them are ionic in nature. Bond strength depends on the lattice enthalpy. CSF is most ionic out of all of them because of Pachans rule, which is understandable. And now, if you see the bond strength out of all of them is going to be answered with respect to lattice enthalpy. Now, lattice enthalpy is something that depends on the size, right? Lattice enthalpy is inversely proportional to size. So when you have smaller cation and smaller anion, the lattice enthalpy is highest because try to understand here that it would be polarizing power and polarizability both would be less there, right? That's one. The second is the ionic character is also very less in the LIF as well. Correct. LIF is not also covalent. It also is a very less ionic. I mean very highly ionic in nature. But the most important thing is that because of the both of them have small sizes, the lattice enthalpy would be the highest in that case. So bond strength of ionic compound, Sean, it would be denoted by lattice. All right. So now, guys, let's go for the melting point trends in here. Now, fluorine to chlorine to bromine to iodine. You always remember this, the melting point trend is always gonna follow this. Now, why is that? Because you know the here it is least polarizable. Least polarizable. I have just taught you in the beginning, and this guy is the most polarizable. So all the elements with iodine would be covalent in nature, not covalent, like covalency would be more, right? More covalence. And the element which has fluorine, they have more ionic character, more covalence. More ionic means more boiling point, right, guys? In the beginning of the class only, I told you this concept. LIF and CSI has very low solubility in water. Again, Sean, it might be helping you to understand this. LIF and CSI has very low solubility in water. Guys, if I talk about fluoride systems, LIF to CSF, if I talk about this, you do understand that out of this, LIF would be the most. So if I just write all the metals down, so sodium, potassium, cesium. So here, guys, the fluorine is constant. So you can understand lithium, sodium, potassium, cesium. These are the metals. So when you're going down the group, what is happening? The polarizing power is decreasing. If the polarizing power is decreasing, that means ionic means covalent character is also decreasing. Covalent character is also decreasing. So guys, with fluorine, with respect to fluorine, LIF is the most covalent. If it is most covalent, then definitely it would be having low solubility in water, right? There is another way, Sean, you can answer this question, like we have just discussed previously. LIF is having the highest lattice enthalpy. It has the highest lattice enthalpy. Lattice enthalpy means you cannot break it down. If you cannot break it down, then definitely it won't be soluble in water. In both the ways, we can answer this question. Correct, guys? CSI, again, the same way. CSI would be the, like if I talk about CSI over here, guys, for iodine system, let's say I have LII, I have CSI. Which one would be the most ionic in nature? Definitely CSI. Even more than most ionic in nature, guys, if you just look into this, CSI has similar sizes, correct? Again, for similar being similar size, it would be having greater bonding, it would be having stronger lattice enthalpy. As a result, so it is better bonding is seen in here. If it has better bonding, then definitely it won't break. If it doesn't break, then definitely not soluble in water. Okay, I'm gonna take that question in a minute, Pratik. Clear, guys? So solubility also you are looking at the lattice enthalpy, means the matching, you can say orbital mismatching, but don't say it, because guys, orbital mismatching is only used for covalent compounds. Okay, but still size mismatching is work. So if you have size matching, then definitely the molecule is strong. If the molecule is strong, then definitely it won't break. If it doesn't break, it won't be solid. That's why LIF and CSI, both of them are size matching. CS is big, I is big. LI is small, I is F is. So the size matching, and because of the size matching, they are having very strong ionic character. I mean, sorry, very strong lattice enthalpy. As a result, they are not gonna, and they are gonna have low solubility. Now, salts of oxoacids. What is the oxoacid? What are the oxoacids? Oxoacids are the acid where the hydrogen is connected with oxygen. That's called oxoacid. Let's say I'm talking about H2SO. In H2SO4, guys, you know that the oxygen and hydrogen bonds are there, and these hydrogens are donatable because there are electronegative oxygens present in there, right? This is called oxoacid. So now, is anything to do with oxo in organic chemistry? No, 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 not that one. This is inorganic acids. All of them are inorganic acids, yeah, right? So example, H2CO3, H2SO4, these are all organic systems, right? So alkali metals are capable of forming these kind of oxides. Now, guys, the important question that can come from here is why the soluble stability of metal carbonate increases down the group. So why the stability of metal carbonate increases down? Again, guys, this is very, very important now. See, let's say I have Li2CO3 and I have CS2. What are they saying? They are saying that CS2CO3 is more stable. Stability is increasing. What do I mean by stability, guys? Where stability means we are talking about bond strength here. What is the parameter that it tells you about bond strength? Size matching. Clearly, guys, lithium is a small cation and carbonate is a big anion. This is small, this is big. So I guess you can understand the concept is just the same. The type of question is changing all the time, right? And cesium over here is a big cation. Carbonate is also big cation. So this is also big. This is also big. So who would be more stable then? This guy would be more stable. That's why the stability. Right now, I'm saying stability. In your exam, they can write thermal stability, same thing. Size mismatch. Size mismatching, higher lattice enthalpy, so would be more like that. Right, guys? Understandable? I guess you can understand there is a particular trend of the questions that they are going to ask you all the time. Now, anomalous property of lithium. Guys, like I said, for every group, the first element is going to be anomalous in nature, right? So lithium for this chapter. For the next chapter, beryllium. For the next chapter, it's going to be boron. And the reasons are also going to be just the same. What are the reasons? Because of small in size. Guys, for every single group, first element would be the smallest of them. So because of small in size. What would happen because they are small? They would be asking for high ionization energy. If somebody asks for high ionization energy, then they would be less reactive, right? In that high polarizing power, being highly polarizable, guys, being highly polarizing, what happens is they are mostly forming covalent compounds. Ionic compounds are always strongly reactive, guys. Covalent compounds are always less reactive. So that's another way to which you can understand they are gonna form covalent. For every single element, you're gonna see that they're gonna form covalent characters. Diagonal relationship with magnesium. For lithium specifically, guys, it is gonna be showing diagonal relationship with magnesium. So lithium and magnesium would be showing similar kind of properties. I'm gonna explain this part a little bit better. Okay. I guess so LiF would be most ionic with respect to whom better. Yeah, it's a comparative question. No? With respect to whom are you saying? You're saying LiF and CSF, CSF is gonna be the most ionic because the polarizing power of cesium is the least. No? Okay. Now, guys, what all anomalous properties is it gonna show? It's exactly what I told you over here. Same thing. They're gonna have the highest boiling point and melting point. They're gonna be the hardest. Hardest means if somebody is small, then they're gonna be hard, right? That way. Lithium is very less reactive, like I told you, that they're asking for high ionization energy, so they're gonna be very less reactive. They're gonna be delicescent in nature. This is something I told you, right? Lithium gonna be having high hydration enthalpy, so it would be making hydrous salts, right? Delicescent means somebody who can get dissolved in water. It takes water from the air and get dissolved in it, guys. So lithium, due to having high hydration enthalpy, it is delicescent in nature. It can form oxide, it can form nitride. I have just told you this, right? I guess earlier in here, I've told you that how lithium can form nitride on the top. I guess you remember that, guys. Somewhere up here, I have told you, right? That NN triple bond can only be broken by lithium. Somewhere in here. Anyways, I couldn't find it anymore. Anyways, guys, this can form Li3N and Li. All right. Only this much is fine. This is not needed. Unstable carbonate bicarbonate. Unstable carbonate bicarbonate, we have just discussed as well, right, guys? That lithium carbonate is not stable thermally. It breaks down. Why? Because the size mismatching, right? Size mismatch. Same thing happens for nitrates as well. For sodium and lithium, you can see that they are breaking down because of the size mismatch. Okay, carbonate and nitrate will be following the same. Now, guys, diagonal relationship with lithium and magnesium, like I said, they are going to show similar kind of property because lithium is there in the group 1's first element, and in group 2, after beryllium, down there we have magnesium. The lithium and magnesium would be having similar properties. Now you can see their sizes are same, their electronegativity are same. They are going to make the similar kind of weak bases. They both react with nitrogen and make nitrides. Okay, these are the things that I already told you. They both of them can make oxide with oxygen. Both have weak carbonate forms because both of them are smaller in size and they don't make a stronger bond with carbonates, right? So both of them breaks down in carbonates, both of them breaks down in nitrates. You can clearly assemble all the reactions that you learned about lithium and make the similar reactions for magnesium to prove this part. Okay, right, guys? Now, in this important compounds, see here there isn't, this part is not at all important. But for your JEE advanced topics, guys, I have given you two videos here. Okay, one of the process is called Solvay process, and the other thing that I have given a video for is the Kastner-Kellner method. This one, Kastner-Kellner. Kastner-Kellner method is still there in the NCERT, but the Solvay process I didn't really find it in the NCERT. So you can watch this video. It's not really important that much, but just give it a go, guys, how the Solvay process works and all in the preparation of these. This part is not at all important, but I've seen question coming in from Solvay process in JEE Advanced in 2020 only. Okay, so you can just check this particular video of Solvay process once. That's all you need to go for that. Okay, nothing other than that is needed. And here for NaCl, so in the compounds of sodium for NaCl, guys, all you have to know is that NaCl, how is NaCl being formed? So you take seawater and evaporate to dryness. From there we get impure NaCl. This impure NaCl is mixed with these compounds, CaCl2, MgCl2, CaSO4, Na2SO4, etc. And they are deliquescent in nature. This was one of the MCQ that came in the last 2022. This exact MCQ came in there. So in the preparation, I don't remember the exact question, but this was in there. So which all things, like maybe it was like, why can't we take the NaCl from just evaporation to dryness of seawater or something like that was mentioned. So that's why I have written this part, guys. So this question have been coming. Okay, so that's all you need from the NaCl side. So uses of NaCl is, so deliquescent in nature is the physical property, right? Somebody, when they are most hydrated, they have high hydration energy, they are deliquescent in nature. So you can understand calcium, magnesium, all of them are smaller in size, right? So they are be definitely having high hydration enthalpy there, correct? Because of now the uses and stuff, guys, just go through it. There is nothing much important in that part. Okay. Now, guys, we'll take a small break of 2 minutes and come back. We'll be starting the group 2 in there. And group 2 would be taking about 15 to 20 minutes. It's going to be a very simple part now after we have done the group 1 now. Okay. Okay. Come back in 2 minutes now. And if you have a doubt, I'm going to be here with you. And rest of you just take a break and come back. And when you come back, guys, one.
Sir, if lithium has more covalent character, then how does it have the highest melting point and boiling point?
Most covalent, I didn't understand your question.
Sir, you said that lithium has the most covalent character, right?
So that depends on with whom are you making the bonding. If lithium iodide you are saying, in that case, it would be very, very covalent. Right. So you have to give me the comparison. With whom are you mentioning this? Lithium halides have high covalent character generally because lithium has high polarizing power. That's true.
So compared to the other group 1 elements, it shows most covalent character?
Comparative because it has high polarizing power. But still, I need a proper comparison. With whom are you trying to compare?
So how does it have like the highest melting point and boiling point?
Only lithium or lithium compounds?
Lithium.
So if I'm talking about only lithium, then why are you taking covalency? Lithium has high boiling point, melting point. That means you're talking about lithium metal in there. It is not a compound. When you're talking about lithium compounds, that's the difference in it.
Oh,
Physical property changes when you make chemical reactions, right?
yeah.
That's what's the question, Ratan? Yeah, what about that? Melting point, boiling point, order of fluorine, chlorine, oxygen, and nitrogen. So, strange question because better fluorine, chlorine, oxygen, and nitrogen, all four of them are gases anyway, right? Then, what's the question? So then, in that case, you you go for the size. Okay, if you have more size, your melting point and boiling point would be more in that case. Ions, let's say they are mixed as compounds. But then again, better see when it's something that you have to understand. When you're mixing them as a compound, na, the properties are not going to be the same. Now depends on what kind of compound you're talking. If you're talking about group one compound, let's say I'm talking about LiF and Li2. Let's say you're comparing these two. Now, if you want to understand the boiling point and melting point, you only tell me which would be having more ionic character. So in Li is common in there. So F minus and O2 minus. This is what you are comparing with now. So who has smaller size? Fluorine has smaller size. So that means oxygen would be comparatively more polarizable. So LiF would be comparatively more ionic than Li2. So that means LiF would be having more boiling. Great. You're confused? Okay. No, see, when you're talking about elements, then you talk about size. When you talk about compound, then you talk about ionic character. For elements, sizes, because van der Waals force depends on size, right? Surface area. Remember, in organic chemistry, we learned it. Physical properties of hydrocarbons. All right, guys, come back now. Let's get over with the group two now. Come back and turn on your cameras, everyone. Come on, guys. This chapter is pretty simple, right? With respect to yesterday's session, they're all connected, all related, right? I'm going to tell you this is the easiest inorganic chapter. There are difficult inorganic chapters out there. Group, uh, group one is the easiest. Like, I mean, the S block is the easiest of them. When you read it, you'll be able to understand it. Again, see, right now you are learning the entire chapter in one session. It would definitely look like there's a lot going on. But you tell me one thing. There are only 2 to 3 logics going on around this entire chapter. One is whenever the bond strength question comes, we talk about lattice enthalpy, means size matching. Whenever solubility question comes, we talk about sizes because smaller is more soluble. Whenever the question related to boiling point, melting point comes, we talk about the ionic character and covalent character. This is where we are moving around in the entire chapter, if you notice. Let's try it now. Okay, the next group, we are going to try it. Okay, so the similar kind of things are going to come in the second group now, and you see whether it comes in the same order or not. Okay, let's see. The entire inorganic is based on periodic table for sure, Smriti. Okay, so guys, who are there in group two? Beta Mange car scooter, Baprazi. So here, we have NS2 configuration, correct? Atomic ionic radii, when you go down the group, it is going to increase. Everything is just going to be same, guys. I'm not teaching you these things. Ionization enthalpy, no change in order. It would be increasing. It would be decreasing like it has happened in group. Hydration enthalpy, exactly the same thing, guys. It is going to decrease when you go down the group because of the size order, correct? It is going to decrease. I'm not teaching you all these things because they are just the same now. Acha, reactions with air and water. Now, guys, here is the first element, beryllium. If beryllium is the first element, he is not going to react, isn't it? Others are going to react, but beryllium is not because it's smaller in size, high ionization energy. The things are going to get repeated. This is what we have just learned in group one, right? So that's why they're saying beryllium and magnesium are kinetically inert. See, beryllium is understandable, it is the first element. Why is magnesium inert? Because it is diagonally in relationship with lithium, right? Now, lithium is inert, so magnesium would also be. Can you understand this, guys? So they're kinetically inert oxygen. But powdered beryllium reacts brilliantly. Why is that, guys? You are increasing the surface area, so definitely the reactions would be increased. So powdered beryllium would definitely react with oxygen to make BeO. Calcium, strontium, barium reacts very well. Definitely because they are asking for less ionization energy. They are bigger in size, so they are going to react faster. Simple. Now, reactivity towards hydrogen, it's the same thing. You get metal hydrides. Same thing, and they are ionic hydrides. What is changing, guys? Only the formula is changing. Either earlier it was lithium H, LiH, now it is MgH2. Nothing else. One thing that I forgot to mention over here, see, beryllium, if I want to make beryllium hydride, it's not going to be an easy job for us, right? You know, beryllium is not going to react. So what am I going to do? So beryllium fluoride is what I'm going to take, and I'm going to react with the strongest reducing agent that I know, lithium aluminum hydride. Only then you can make beryllium hydride. For others, you can just react with hydrogen, they would form the hydride, but not for beryllium. You need the strongest reagent out there, and you form the hydrides for beryllium only. Okay. Reactivity towards acid, guys, as usual, whenever metals are reacted to with acids, they are going to get hydrogen gases, right? Nothing new with that. Reducing power, like I told you, every single metals have high reducing power in there. Now, reducing power is more than corresponding alkali metals. So now we are comparing it. See, I'm saying that alkaline earth metal has more reducing power, and it is very much understandable because, guys, when we are moving from alkali metal group 1 to group 2, when we are moving from group 1 to group 2, what's going to happen over here? They are saying that the reducing power is increased, is more. That means what I'm trying to tell you over here is, guys, don't get confused with lithium over here. Lithium is the most reducing anyway with respect to everyone out there. Now, why is the reducing power increasing for group 2 element? Now, you have to understand this part here. See, when I'm talking about reduction power, what I'm talking about is when, let's say, I have a metal, I am reducing. That means I am donating the electrons. Correct? It's how the group 2 element works. For group 1 element, how should I write the equation? I am reducing, that means I am releasing electron again. This how should I write? Now see, none of the molecules are stable in this. So what is the energy I need, guys? I need ionization energy. Here also I need ionization energy. But none of the molecules none of the atoms are stable in the ionic state. So what do we have to do for that there? We have to dissolve them in water, guys. Right? Only then an ion can be stable. Now you dissolve it in water, you get N plus aqueous, and you dissolve this guy in water. Now my question is, guys, who's gonna be a stronger reducing agent? That's the question. Now see, answer is group. Why is that? Because see, group 2 hydration enthalpy would be more. Why? Because the charge. So for group 2, delta H hydration is greater than the group 1 delta H hydration. Because, guys, if you have more charge, you have more ionic character. If you have more ionic character, you are going to be more soluble. Correct? So if group 2 has high hydration enthalpy, then group 2 is the one who's going to be making more and more reaction. It would be making more and more cations. It would be releasing more and more electrons because the cation is very, very stable underwater, right? That's why group 2 elements are more reducing than 1 elements. Okay. So what are you going to write here? You're going to write like this. So for reduction, there are two energies involved in here. One is ionization energy and the other one is delta H hydration. For group 2, delta H hydration being very high, it has high reducing. It has high reducing because the delta H hydration. All right, guys. So this is the answer to the. So let's see, I'm writing that. The reducing nature is because of the high hydration enthalpy. Guys, this kind of question can come in assertion reason type. Okay. Other than this hydration enthalpy, there is no other reason behind this high reducing power of heat. Okay, this is the only reason why. But group has only filled shell, right? So generally it should be anyway react lesser than group 1, right? Exactly, Swaraj. You are completely right. But like I said, now it's the mixture of two energies. You are completely right that group 2 would be taking higher ionization energy. So it's like we are comparing them. Let's say for group 1, we are adding ionization energy and hydration enthalpy. And group 2 also we are adding ionization energy and hydration. Let's say for group 1, the ionization energy 10 and the hydration enthalpy is, let's say, 20. So the total value is 30. Let's say. Okay, there is one thing. Ionization energy is endothermic, hydration enthalpy is exothermic. So the value is minus 10 K. For group 2, it's true that the ionization enthalpy would be more, but the hydration enthalpy would also be more. So the overall value is more than the. That's why they are higher names. Understood? Okay. Now, guys, I guess I don't have to explain this anymore. How do the liquid ammonia solution work? Again, guys, it's gonna donate the electrons. The electrons are gonna be free. They are gonna show the color. Just the same thing. You can see ENH3 whole Y. I don't know how many ammonias are gonna be there. So I'm just writing as well. Okay. This is what gonna be show the color. But if I add more and more metal, would it get intensified? No, it would be getting pale and pale because the electrons are now gonna get paired up. Because of pairing up, the color would less. Right, guys? You can see the similarity. Then go for the uses again, like what all uses are there. Magnesium alloy are in the aircraft. Magnesium is as antacids. Let's go for the uses. Okay. Now general characteristics, guys. See now, beryllium oxide is covalent in nature. It's not a news to you. You know that beryllium has high polarizing power, Be2 plus, just like Li2 plus. So all the compounds would be covalent in nature, polarizing power. So again, due to Fajan's rule, it's gonna be covalent in nature. BeO is amphoteric in nature. That means when you react BeO with acid, you'd get salt and water. And if you react this BeO with base, then also you would get salt and water. My point is, guys, you need to know this compound when it reacts with base. BeOH whole 4. Okay, BeCl2 is not the base. This compound is the thing that we need. Okay, so with base, you remember this reaction. Acid is something else. Now, guys, let's talk about solubility, thermal stability, and basic character. Let's talk about one by one. Let's say I'm talking about BeCO3. Would it be thermally stable? I'm going to write it down now in the chat. BeCO3, would it be thermally stable or not? What's going to be the answer to this? Very, very unstable because of the size mismatching. So how would it break? It would break into, so you know, all the carbonates break into carbon dioxide and metal oxide, right? Learned it back then in grade 10 only. All the things are similar, beta. That is not only the beryllium, everything is similar, right? Then again, if I talk about basic character, so guys, let's talk about the basic character of MgOH whole twice to BaOH whole twice. What is happening there? So when you are moving from Mg to Ba, what is happening? The size is increasing. Correct? Now Mg is a small cation. What about OH minus, guys? Does it look like a big cation? No, no. It is also small. So MgOH whole twice, it's a strong element. Like it's a strong element. It's not gonna break. But BaOH whole twice, it is weak. So BaOH whole twice would break into Ba2 plus and 2OH minus. That means it is gonna release a lot of OH minus. That means it's gonna be highly basic. Understood, guys? So again, you can see that there is a particular pattern that they are following. When they're talking about basicity, you can understand who is more basic, whoever releases more OH, right? So beryllium, this bonding is going to be the weakest, so it is going to break more, so it's going to be beryllium. Yes, Pratush.
Sir, what is the reason because why it is weak? Due to
Which
the
one is weak?
difference.
Size mismatching again. If you see barium is the last metal of that. So barium size is the one.
Sir, but you told that when it is ionic, the compound is ionic, so we will not see for the size.
No, I said we are not going to see orbital matching. Because orbital matching and orbital mismatching, like overlapping, happens for covalent compounds, right? I told you for ionic compound, instead of calling it orbital matching, call it lattice energy. Size effect is there in all the kinds of compounds. Size should be similar. That is there for covalent as well as ionic compound. But for covalent compound, we call it orbital overlap. For ionic character, we call them lattice energy. That's the only wording that you have to play with. The reasoning is just the same in both the cases. Just we need to change the words that we use.
Sir, lattice energy, if I'm not wrong, then it is that the energy given out by the compounds, so it can become stable, right?
The energy given up by the compounds when the molecule is getting formed
Yes,
from
sir.
the
So it
ions.
becomes stable after that, giving
Right.
out the energy, right?
Yeah, you can say it. Right. It's like it's a bond energy. But again, we cannot use the bond word because ionic compound doesn't have a bond. For covalent, we call it bond energy. For ionic, we call it lattice. So when you are trying to make a bond, I mean ionic compound, the energy that is getting released, that's called lattice energy. So when you have size matching, then it's a better bonding. I mean, again, better lattice. If it's a better lattice, then more energy is being